Okay, so now I want to switch to the sample quiz. And the question, the most important question is the simulation question, the OS simulation question, because we haven't done a similar question before. So you will have an OS simulation question like this in the quiz. So what do we mean by simulation? Drawing a timing diagram that will show how an operating system will handle a couple of processes. So we have a description for a couple of processes. P1, process P1 has a 30 millisecond CPU burst, followed by a 200 millisecond I/O request. It's not to scale. But, now, I want to note here that we're saying that the I/O request is going to take 200 milliseconds. Now, in a real system, the time that it takes the I/O device to process a request is going to depend, of course, on the speed of the device, but it will also depend on the queue for that device. So the device will not necessarily be ready for this request because it may have other processes in the queue. So what this 200 means is that once the I/O device starts servicing this request, it's going to take 200 milliseconds. Okay? And then there is a CPU burst of 20 milliseconds. And P2 will have a CPU burst of 60 milliseconds, followed by an I/O request of 70, followed by a CPU burst of 10, I think. 10. So these are the processes. Now we need to draw the timing diagram of the operating system. Now there are lots of important information here. I/O request, each I/O request goes to a different device. So we are assuming that this I/O request and this I/O request are going to different devices. So the simulation will change completely if they go to the same device. The kernel starts each I/O request right at the beginning of the kernel task. So this is an idealization. So these idealizations are basically to simplify things. So we'll assume that the kernel starts the I/O request right at the beginning, even though in reality, the kernel will take some time before it sends the I/O request to the I/O device, and the I/O device starts processing. So there will be a delay because in reality things are not magic. But we are simplifying things here to focus on the concepts. The I/O device will start processing a queued request as soon as the current request is done. Again, there is a delay that we are ignoring here. So once the I/O device is done with one request, it's going to start processing the next request immediately, which means that we are ignoring the delay. Now, whenever P1 and P2 are both ready, the scheduler will give the CPU to P1. So this is the scheduling strategy. So this is something that we need to pay attention to, because the scheduling strategy will be different. So you should be able to do this with different scheduling strategies. The scheduling strategy is given to you. We're given the scheduling strategy, but you have to draw the timing diagram accordingly. The time quantum is 50 milliseconds, so time quantum equals 50 milliseconds. The kernel time, including initiation of I/O requests, scheduling, and context switching, is 10 milliseconds. So kernel time is 10 milliseconds, always. And again, this is a simplification. Ignore any delay or transition time that we have ignored in class. Okay, so now, initially, we have the kernel. So at time 0, the kernel is on the CPU. CPU. The kernel is on the CPU, and it will be there for 10 milliseconds. Then the kernel now will have to select a process to give the CPU to. Now, which process is ready? Initially both are ready. So the CPU, according to the scheduling strategy, it will give the CPU to P1. Now, for how long will P1 have the CPU?
30 seconds.
Yeah. So the point here is that after 30 milliseconds, it's going to request I/O. The time quantum is 50. So in this case, P1 will not use its entire time quantum. Right? So one of the mistakes that I see that some students make are, giving P1 50. No. So the system is not going to get. The system is going to give it up to 50, but it's not going to use the 50. It will request I/O after 30. So this is 30. Then the kernel is in charge, and the kernel will send the request to the I/O device, and this is a long I/O request. So this is I/O, and the I/O is now servicing P1. Then after 10 milliseconds, now the kernel will look at the ready queue, and it will pick a process that is ready. Now, which processes are ready now? P2 is the only process that it's ready, so this makes it easy for the kernel. The kernel will not have to choose. There's only one ready process, so it will give the CPU to P2. Then for how long will P2 have the CPU?
50.
For 50, yeah. So this is an important point. It's going to have it for 50, because the time quantum is 50. So its CPU burst is 60, but the system is going to give it 50. Then it will get another time quantum. Then the kernel gets the CPU. Then it will look at the ready queue, and it will find P2 only in the ready queue. So it's going to give P2 another time quantum. So it's going to give it 50. But will P2 use the 50?
No.
No, it will only use 10 of them. Okay. It will use 10 milliseconds. Then it's going to request I/O. So now this I/O request is going to a different I/O device, which means that, assuming that all the I/O device queues are empty, this is going to start, the I/O device will start processing this immediately. So at this time, P2 will be serviced by the I/O device. So now we'll call this I/O1, this is I/O2. Now, the kernel will look at the ready queue. And what will the ready queue look like at this point? Yeah, it will be empty. So the kernel will not find any process to give the CPU to, so the kernel will will keep the CPU. There's no other choice. So this is idle time. Kernel has the CPU until a process becomes ready. Now, which process will complete first?
P2.
Yeah, P2. So this is P2 is 70, this is 120. So here, this is like 80. So P1 will need 120 more. 120 to go, and this needs 70, so P2 will finish first. So let's say that this is 70. Now when, after 70, an interrupt will happen, and the system will invoke the kernel, and the kernel will process that I/O request. So, we can give some more kernel time here, because more realistically, the kernel will need to process the interrupt. It will need to service the interrupt that will get generated by the I/O device. So let's put the kernel time here. So the kernel will get the CPU, it will do the copying, and it will look at the ready queue. Then it will give the CPU to which process?
P2.
P2. Because P2 is now the only process that is ready. Then P2 will have the CPU for how long?
10.
For 10 only. Then the kernel will get the CPU back. And the kernel will be waiting for, so this is
24.
80, this is 70. And so we need 50 more, right? 80, 70, so we need 50 more. 20, so we need, the kernel will have it for 30. Until this request completes, then the kernel will have it again. And it will give the CPU to P1. And P1 will have it for 20. Okay. So any questions on this timing diagram? Yes.
When the kernel has control for the idle time, is that we don't need to identify that that's split into 10 milliseconds of processing and then 60 milliseconds of idling? We can just call it as one?
Yeah, it's kernel time. So in fact, yeah, so it's, so the 10 millisecond is the kernel time when the kernel manages, when the kernel finds a ready process and gives it the CPU. But if there is no ready process, the kernel will just keep it.
We
will
can
just keep the CPU.
So we can just identify that as one block?
Yes.
Okay.
Yeah, it's just kernel time. Yeah.
I think it's the same thing, but basically, so between the two P2 for 10 milliseconds, you could just make a kernel that says 80, or directly above the I/O time for P2.
Oh, here?
Yeah, could that just be 80?
Yeah, that's fine. That's fine. We're just trying to, mark this to clearly simulate the event of I/O completion. So this line basically, makes it clearer that there is I/O completion and this is, the kernel. Of course, there will be, it's all kernel time, but here we're saying that the kernel now is responding to an I/O completion interrupt. Okay. Okay, any questions, any further questions? Yeah.
When I did mine, I just worked mine as one I/O. If you have it set to where it goes to a different device, do you want there to be two separate I/Os?
So they are different devices.
Okay.
So you can, well, in fact, now we will do it with one device, but it will be a different problem.
Right, okay.
Okay, so it's two different devices. Now we will do it with one I/O device, assuming that they both go to the same device. The solution will change. Right? Okay, so now, are there any questions before we do it with one I/O device? Okay, now suppose that we change the question so that both I/O requests go to the same device. Now what will happen? So the change will start here. Okay, so they both go to the same I/O device, and this stuff will change. So now at this point, P2 is requesting I/O, but the device is not available. So P2 will be queued, will get queued, and in fact, it will not get the device until this is completely done. So, so we need 80 and another 70. Then the I/O device will be available for P2. So here the kernel is gonna send it to the device, but the device will not start working on it until it's done with the current request. So the device does one request at a time. So now the kernel is, during this time the kernel is idle. So all of this is going to be idle kernel time. Obviously this is going to take longer because you have less resources. So you only have one I/O device. Now the kernel cannot find any ready process. Both of them are waiting. One is getting service, the other one is in the queue. Now when P1 completes, the kernel is going to intervene and is going to give the CPU to P1 for 20 milliseconds. To P1 for 20 milliseconds. Then, this is going to be another 70. So the kernel will keep the CPU for 10 plus 20, that's 30. So it will keep it for 40. 40 milliseconds. Then P2 will complete. The kernel will respond to the interrupt. And it will give the CPU to P2 for 10 milliseconds. Okay. So the idea is, P2 will be waiting until the I/O device is done with P1, and during this long period of time, the kernel will not find any ready process.
In the first I/O, where you have process 1, you have 80 and 70. That should just be a total of 200, correct?
Oh, yeah, sorry, yeah, it's not 150, it's 200. In fact, so this should be 120. Yeah, right. Sorry. Yeah, so this is 120, so this means that this kernel time will be 120. Yeah, so this is long. Yeah. Oh. Yes, you are right. So this is 80, 120. Yeah. Okay, any questions on this? Okay, so this is these timing diagrams simulate how the kernel works, how it handles multiple processes. Now let's look at this question. So this is about state transitions. So you are given a certain event, and then the question is, from which state to which state does the process transition when that event takes place, and in which queue will the process be placed afterwards? And make sure that you put something here. So if there is no queue, say none, as it says here. If none, enter none. Because none is leaving this empty means that you don't know. But if you say none, then you know that there is no queue. Time quantum expires. So when the time quantum expires, the state changes from running to ready. And the queue in this case will be
Ready queue.
the ready queue. When an I/O device completes a process's request, we transition from waiting to ready, and the queue again will be the ready queue. Now, what's the event that will cause transition from ready to running? What event?
The scheduler.
Yeah, the scheduled dispatch. There is no other event. So the only way to go from ready to running is when the scheduler decides or selects this process for the CPU. So that's scheduler dispatch, or scheduler selecting the process for the CPU. And then the process will be running. And in which queue will the process be? None. So the answer here is none.
So when I did this, I looked at the second one, the I/O device completes a request. And I thought that the transition was from another process that was in the CPU. So I was thinking you could be looking at that from considering a process in the CPU or the process that just completed in the I/O device. So I thought that.
Ah, which process we are referring to?
Yeah, exactly.
Yeah, so I thought that it's obvious that we're talking about the process, we're referring to the same process for which the I/O device completed processing an I/O request. So I/O device completes a process's request, so we are referring to this process. Yeah, not to another process that is on the CPU. I don't know, nobody has ever interpreted this.
I wrote down both ways, just in case.
Yeah, so, okay, yeah, so here, okay, so there is only one process. So this, in this question, there is only one process that we are referring to. And here it's the process for which the I/O request belongs.
Thank you.
Any questions? Okay, so we still have a couple of minutes, so we'll go through question 1 and question 2. Now, comparing OS structures, compare from the given point of view. So monolithic versus microkernel from performance point of view. Which one is better and why?
Mono.
Yeah, why?
It doesn't have to go, they can more, when it passes messages, it can just go directly from one, not layer, but from one application to the kernel.
Okay, so no, this is not true. It doesn't pass messages.
No.
Monolithic does not pass messages at all. Yeah.
Every piece communicating with another piece. The microkernel has to pass messages back and forth to get to like methods outside.
So
of
there
it.
is no message passing at all. So in monolithic, there is no message passing. In microkernel, there is message passing. And that's why microkernel is slower. So in the microkernel, there is message passing. In the monolithic, there is no message passing. And that's why monolithic is faster. So by the way, whenever you compare two different things, make sure that you say something about each one of them. Don't just say, that this is faster because this does this, but tell us what happens on the other side.